Today I'm going to talk about something that most of you have probably heard me talk about at least once, if not too many times, which is an update on where we are with Project Valhalla. So I've been talking about Project Valhalla, as most of you know, for the last 100 years. And some of you are probably thinking, are you guys ever going to deliver anything, or are you just going to keep talking about it? So today I'm going to do an update on where we actually are. Which is to say, we have some things working, we have some things on which we're not done, but it's sort of, I think we've recently reached an inflection point where things have become usable for this audience to start experimenting with. So, you know, I work at Oracle. Okay, so for the one or two of you who haven't seen one of my Valhalla talks before, I'll just give a brief background on what Valhalla is. I promise it will only be like 3 slides. So the main goal of Project Valhalla is to sort of reboot the JVM's relationship with data in memory, and in particular to enable denser and flatter layouts of object graphs in memory. And the key thing that we had to tame in order to succeed at that is the fact that everything is an object and every object has identity. And you know, in 1995, everything is an object and objects have identity was a totally sensible way to solve all the world's complexity. But in reality, you know, not every object wants or needs identity, and we don't think necessarily every object should be paying for it. So object identity serves mutability, it serves layout polymorphism, it serves locking, and a lot of classes use one or all of the above things. And a lot of classes don't. A lot of classes that just represent ordinary pure data don't care about any of these things, and unfortunately they're still paying for it. And it becomes, you know, we've done various experiments with, say, escape analysis to try to determine, you know, can we prove at compile time that the object identity isn't observed and therefore we can optimize better? And sometimes we can, but that's a very fragile optimization. It's basically impractical to dynamically determine that no one will ever use the identity of this object. So if we can't determine this, the standard move is to ask the programmer for help, saying, can you tell us something about this class that allows us to make a broader range of assumptions about it? And so, sounds really easy, right? We need one new keyword, whether it's value or inline or whatever, apply that to a class, and you're done, right? So why is this taking so long? From the perspective of what we want to have happen in memory, is if you have an array of XY point objects, what you get today is you get an array which is an object with a header, and its contents are pointers, and those pointers point to other objects with headers. And your XY data is strewn all over memory according to the whim of the garbage collector, and you're not going to get either good density because you're paying all of this overhead for object headers and pointers, and you're not going to get good locality. A lot of the time, when people want an array of XY points, what they really want is the layout on the bottom, which is just lay out XY, 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 and be done with it. So that's what we assume the user wants, and we would like to be able to take cues that the user has given us and give us that layout. So who cares? Who cares about value types? My claim, self-serving claim perhaps, is that everybody cares about value types, at least indirectly. So certainly there are going to be some application writers who really would love to have this better control over layout and memory and be able to fit more data in memory and because of better density and all of that. And that's generally a relatively small subset of Java developers that are working with very large data sets. But library writers, I think, are very interested in what value types have to offer because it allows you to use all of the traditional abstractive tools that the language gives you without paying the runtime cost of taking an extra indirection every time someone uses your abstraction. So library classes like optional or cursors or better numerics don't want to have to pay the object tax. And similarly, there's a lot of people in this room who write compilers for languages that aren't Java, and sometimes they find themselves in the unfortunate situation of having numeric types that aren't exactly the same as Java's primitives, and again, that's an area where they have to pay the object tax, and that means every one of their users is paying the object tax. So by making it possible for library writers and compiler writers to have a more efficient substrate they can target, my claim is everybody wins because everybody's code just gets faster. So we approach this problem sort of like drilling the tunnel across the English Channel, where we have to bridge the language side and the VM side, and it's sort of, you have like, a number of impossible problems on both sides, and so we started exploring this problem from both ends. So we did some early prototypes that were largely language only, aimed at exploring the language implications specifically for generics. And we learned a lot from those prototypes. We still have more to learn. They're not solved problems yet. And at the same time, we started drilling from the other side, which is the VM side. Last year at JVMLS, we had a prototype called MVT, Minimal Value Types, which was truly minimal, and probably none of you tried it because it was pretty painful to program with. But it was aimed at proving that it was possible to get these layout benefits at all. And now the most recent prototype that we've just recently published, called L2, is actually, I would say, the first usable prototype for the folks like those that are in this room who are compiler writers and data structure writers, and it has VM support and Java-C compiler support so that you can actually start to write data structures using value types. We still don't have support for specialized generics yet or compatible migration. This is, there's lots more rock to bore through here, but at least the boring from both sides is starting to bear some fruit. So to sort of characterize what we sort of unveiled last year that didn't work, and we were kind of suspected it wouldn't work, but it was the easy first prototype to do, was what we were calling L-World, which is to say, the hypothesis was, imagine that value types are basically like programmable primitives. So if you look at the way the JVM treats data types, we have a carrier type for each primitive, I for int, j for long, L for oop. And we said, all right, let's have a new carrier. We called it Q for no good reason. And that'll be the carrier for value types. And similarly, we have these typed bytecodes, iload to push an int on the stack, lload to push a long on the stack, et cetera. And for all of those iload, ireturn, istore, iaload bytecodes, we had Q variants. So there were probably like a dozen new bytecodes. And there was no relationship between value types and Java-Lang object. So we took the idea of codes like a class works like an int very literally, where we took the works like an int all the way down into the middle, and this worked for some definition of worked, but we found that it was painful for a lot of the things that we care about a lot, like it made the existing divide between primitives and references worse. Well, that's something that we'd like to make better, not worse, so that was bad. And it was extremely painful for migrating classes from reference types to value types, and it was painful for specialization as well. And so, based on this, we sort of rethought the story and said, okay, let's look at it from the other perspective, and this is what we call the L-World hypothesis, which we started to talk about last year, which is to say, rather than treat values as being programmable primitives, let's treat them as more like restricted objects. And they use the same A bytecodes, A load, A store, A return. Value types are subtype of object. Value arrays are subtype of object array. We actually did keep the Q carrier around in the type descriptor language, but it kind of got repurposed. And so where this left us was a much, much better programming model because it brought us back to almost everything as an object. We still have the asterisk on that for primitives, but we'll get there. But it also had a lot more impact on the VM because the VM now had to deal with the A-load might be pushing something that is, one word on the stack because it's a pointer to a reference object, and it might be pushing more than that on the stack. And so this trade-off between the programming model and what we're asking the VM to do for us is a recurring theme throughout Project Valhalla. So the benefits of this L-World approach are mostly in the programming model. You get simpler migration. Type descriptors don't gratuitously change from L to Q necessarily. We had a terrible problem with arrays where just like int array is not a subtype of object array, if value arrays were not subtypes of object arrays, you had terrible problems both writing generic code and writing code that was dynamically typed, that wanted to deal an object and object array. And similarly, in the old world, specialization was painful. We had to specialize basically every bytecode of the class. In L-World, specialization can proceed entirely on the constant pool, and the bytecodes are unaffected, which not only is cleaner and allows the VM to share a lot more between different specializations of a given class, but it also means that the VM has the option to specialize lazily and not have to specialize before the first time you instantiate a specialized generic. By rejiggering the model, we put more work on the VM. We got a programming model that is more familiar to Java developers, hasn't yet addressed the object primitive divide, but one impossible problem at a time. So the question that we're sort of struggling with now, and this is sort of the, we're at this crossroads where we have to evaluate whether we're going to get the benefits that we had hoped we would get, is the cost of the L-World hypothesis, which is to make values more like objects, puts a bunch of new costs on the VM, array covariance, for example. And there are certain operations that are currently total on object, like locking. Well, now what happens if someone assigns a value to object, and that's allowed by subtyping, and then tries to lock on that object? What's supposed to happen? There's a number of nasty questions that this raises, and a lot of these things, the answer ends up being more work for the JVM. And so each of these, a little more work for the JVM, also has a cost because we're loading more complexity onto bytecodes like AA store and AComp and things like that. And each of those is stealing away a little performance from the performance that we were hoping to get by having value types. And so we're at the point where we're finally starting to be able to measure both sides of the equation, the cost and benefit, and we certainly hope that what comes out is a sensible balance. So where are we now? We picked as a numbering scheme milestones 1 through 100 just to give ourselves some room to work. And we picked a sort of logarithmic scale where we said, L1 should be the minimal thing that's like usable that you could write a program with, and L10 should be the minimal thing that we are comfortable enough with that we could take it to a preview feature in a Java release. And L100 brings in, all of the things that we've been driving towards, like migration compatibility and specialized generics and all of that. And where are we now? Well, we're at L2 now. EA binaries for L2 went up on jdk.java.net just like a couple of weeks ago. And this is actually a big deal because this is a usable programming model. You can declare and use value types, which we're calling inline classes now. You can have generics over value types. Currently they're erased, they're not yet specialized. And we have optimizations implemented for object layout, for compilation, for calling convention, so that when you pass a value from one method to another, it gets scalarized and the fields get passed in registers rather than passing a pointer around. And so we're finally at the point where someone like this morning Gotti was talking about their hash array map try implementation. You could actually start trying to implement that with value types and see how it would work. Or like the capsule library that Michael Steendorfer talked about in this room probably 4 years ago? Something like that. We're very hopeful that Michael will pick that work up and come back in just a few weeks and say, hey, I tried it with value types and it's awesome. We can hope, right? So, for people who are building data structures or building compilers, it's finally at the point where it's ready for experimentation, and I beg you all to give it a try. So let's talk about what we've got implemented. Optimizations for layout. Value types are routinely flattened into other objects, into arrays, and their object header is compressed away. When I say routinely, it doesn't always happen because the VM may say, oh, this value type has 800 fields. There's no point in inlining that. I'm just going to continue to represent that by a pointer. And that's a choice the VM's allowed to make, and that's fine. Instantiation of value types is routinely optimized away and scalarized into fields. Value classes are known by the VM to be monomorphic, so we get good method dispatch performance. And we have calling convention optimizations where values are routinely scalarized and passed as fields between methods, even if they're not inlined all the way through. So there's like a lot of work has been done on the VM optimization side. And to that end, I have some terrible benchmarks. If Sergey saw my benchmarks, he would be appalled. But I ran, this was just like last Friday, because I do things at the last minute sometimes. I wrote some quick and dirty JMH benchmarks to just try to get a feel for what kind of optimizations are possible. So the first one was actually one that Mark did at the Java 1 keynote last year, which is to take 500 by 500 complex matrix multiplication. That's an example of something that is embarrassingly valueizable. That so much of the overhead of that has to do with the object allocation and indirection costs. And on my machine, like I said, a few runs, not particularly rigorous methodology, I saw like a 6x throughput improvement. I know we've seen other benchmarks that give us better than that, and like a 1000x improvement on allocation, which makes total sense because this implementation is doing nothing but allocating lots of complex numbers. But that's kind of a cheaty example because it's sort of a pathologically good situation. So, I ran a few others where I took the array of points example that they had pictures of, earlier, and did allocated one of these, initialize it, and then just like add up the x and y components. And with a hand unrolled loop, nothing fancy. And I saw in that case something like a 3.5x performance improvement. So since there's no allocation involved in this particular workload, this is all just due to better locality. That's maybe a little bit less cheaty of an example. I did the same thing with a stream, and I got an anomalously good 12x faster, which I think is probably because the value stream ended up with a simpler enough bytecode that we got better inlining from the JIT, because I wouldn't have expected such a good speed up. But the point is not so much, take this number to the bank, as much as this is starting to look like idiomatic Java code that ordinary users would write to do business logic, and we're seeing substantial speedups by using values over using reference carriers. So it's encouraging, but obviously these are quick and dirty benchmarks. And similarly, I did another version of the same thing where I used an immutable accumulator object, and obviously with a value version of that, you're going to see a lot. You're not going to see any allocation, and you're going to get good scalarization. And again, I got like an 8x improvement there. And so I can't conclude very much from this other than there's reason for optimism, and it kind of validates the approach that we took in this project going in, which is we want to stop putting users in the position where they feel like they have to choose between abstraction and performance. Because if you give people that choice, they're going to choose wrong some percentage of the time. If the right way turns out to be the fast way, then you've aligned these motivations, and you have less motivation for people to like garble up their code with what they think are optimizations. So encouraging numbers, but like I said, these are my terrible benchmarks, so I wouldn't put a lot of faith in them. All right, so let me talk a little bit briefly about the programming model, since I've told you that it's like ready to write programs with. So let me talk about the programming model that you get to write programs with. So at the source level, constructing a value, writing a constructor for a value class looks just like a constructor for any other class. It gets translated differently because the one place where there are new bytecodes for value types is in the initialization of values. So when you say new foo in today's Java, you end up, that translates into a new bytecode which creates an uninitialized object and then a dupe, and then you do an invoke special on the constructor to fill in its state. And many painful verifier bugs and security bugs have come out of this way of initializing things. When when you instantiate a value type, it gets translated into something much more sane, which is an invoke static of a factory method. So when you write a constructor for a value type, the compiler is going to translate it into a static method that's suitable for, being called with invoke static. And that method itself uses the two new bytecodes that we've added. One is called default value, which means get me the default version, the all zeros version of this value, and then with field, which is, okay, take the value that's on the top of the stack and give me an equivalent one, except with this one field mutated. So the constructor will get translated into default value with field, with field, with field, and then the JIT will say, oh, I don't need to do that in that many steps. I can be a lot more efficient about that. So from the outside and from the source perspective, they look just like regular objects. A lot of work went into the array implementation to make arrays of value types covariant with object arrays. So for any given value type V array is a subtype of object array. We dragged our feet on this for a long time. We tried really hard to avoid paying this price, and we just kept finding ourselves boxed in by the way everybody codes in Java. And we want the way people code in Java to carry naturally over into the values programming model. And so we had to suck it up and pay the cost of array covariance so that people could continue to write methods that take object array, which means pass me an array of anything, or generic code that assumes that T-array and object array are the same representation, or to be able to migrate classes to value types, or to be able to migrate erase generics to specialized generics. So there was this widespread assumption that is embodied in almost every source file in the world, and we eventually gave up fighting it and just sort of let it wash over us. Every variable has a default value, and that's the value that an uninitialized field will have or an uninitialized array element will have. And for the types that we know about, it's always some flavor of 0. Default value for int is 0. Default value for a reference is null. Default value for a Boolean is false. And the rule is basically the VM initializes everything with zeros so that you at least don't get stupid values. And so it made sense for us to continue to follow this rule for value types, which is to say the default value for a value type is the one all of whose fields have their default value, and recursively on the way down. And if you want to denote I want the default value of type foo, you can say that in source with foo.default, or in generic code with t.default. So if you want to reinitialize a variable to its default state, you can say x equals t.default, much the way generic code says x equals null today. Now, this makes some work for authors of value types, because every once in a while you have a value type for whom this 0 value is not a sensible member of your domain. Like, for example, you have a value type for rational, whose representation is numerator denominator, and 0 over 0 is a stupid rational that will blow up anytime someone tries to use it. And that does mean some extra work for authors of these value classes. And that was a painful trade-off. We went round and around. Lots of people said, oh, couldn't I write a no-OR constructor and that will be the default value for this type? And we read an excellent series of blog posts by Eric Lippert, about how they tried this in C# and it didn't work very well. And we were chastened by the experience of someone who had tried to do that before and came up with some strange anomalies. So value types are supposed to be routinely flattened into something that contains them, whether it be another value or an object type or an array type. But rather than say flattened, we really should say flattenable, because we don't necessarily want to flatten 100% of the time. Sometimes the VM may say, this value is too big. You'd be much better off representing it as a pointer. And we want the VM to have that choice. And similarly, maybe we want atomicity. We want to be able to have a fast cas on something. And again, it makes more sense to represent it as a pointer that way. And so we want to leave the VM that flexibility, but we also want to leave the user that flexibility to say, yes, this is a value type, but this value type field in this bigger thing shouldn't get flattened, or in this array shouldn't get flattened, for any number of good reasons that the user might have. Like, for example, maybe it's a value type that has a lot of fields, and I'm allocating what I expect to be a sparse array. I would rather allocate an array of n pointers than 12n individual fields, most of which will be zeros. And so it's the difference between saying struct point P and struct point star P and C, and we think that users are going to want the same flexibility at the use site that, that they would have in C for this, where we want to have good defaults. We want the default to be flattenable and let the VM use its judgment there, but we also, the users may want to have some control over that. That means we need a way to denote it in the source language. The way that we have settled on this for purposes of the current prototype, this isn't necessarily a final decision, is to say for value type V, there's a corresponding type V question mark, which means V or null. And we use that nullability as a signal for flattenability, as a signal of saying, I don't want flattening here. I don't, and we can use the same thing for specialized generics to say, I don't want specialization here. That may or may not be the right answer, but it's the point we're currently exploring. And so, we use the, we currently use the rubric that a nullable type should use the pointer contract rather than the inline contract for embedding a value type. And like I said, might be the right thing, might be the wrong thing. I'm hoping that some of you will tell us. Generics are many stories here, so we've divided them into at least two, which is the erased generics that we have today and the specialized generics we'd like to have tomorrow. Because we're not going to have specialized generics out of the gate, it means that we need to be mindful of the denotative distinction between an array list of flattened point and an array list of erased point. So in the meantime, all we have is erased generics, and we've again chosen to use the nullable type convention, where you say, if you want an erased list of values, you say foo of v question. And you're saying, I want this to be an erased list because this is a generic over a nullable type. Again, that may or may not be the ideal way to send that signal, but that's how it works for now, and that leaves room for foo of v to mean specialized. So we're currently holding that syntax for, that it can't be used now, so that when it becomes valid later, we don't have existing utterances of foo of v spontaneously changing their meaning. So one of the things we've been talking about recently, and this is not something, now we've left the range of what's in L2 and started to talk about the things that are up next on the discussion list, is do we need some new top types? Do we need a top type, a reference type, and value types? And I kind of think we do, because we use types in all manner of useful ways to indicate our intent. So if, for example, we have a method that's going to take an object and it's planning to lock on that object, you would like to be able to say in the static type system, in the way the compiler can enforce, don't pass me something whose lock operation is going to throw. And so one way we could stack that is to say, there are some new types, they're subtype of object, call them ref object and val object, and all traditional classes are going to be subtypes of ref object, and all the value classes will be subtypes of val object. And there's a relatively small set of rules for how this would work, and it seems like a reasonable way to stack it. And what that allows you to do is have the object model reflect the reality that not all objects are created equal, right? So it allows us to ask questions dynamically like, is X instance of ref object? It allows us to use these types and signatures where I say, I'm returning a ref object, therefore it's nullable and it's safe for you to lock on. Or I only take a ref object. Or I have a generic class whose bound is ref object. Don't try to instantiate this with a value type, because that's not going to work. Given that we use types for all of these things already, it makes sense that types be the natural way to express these things. So this is one of the things that we are currently discussing, and that you might hear more about as time goes forward. One of the most persistent pain points in this entire investigation is the slippery nature of null and nullity and nullability. Certainly it's a sensible default to say values can't be null. There are some values like int, for example, that uses all their bit patterns and doesn't want to take on extra space to represent the notion of there's no int here. And having nullity be this sort of out-of-band signal to the representation is one of these things that undermines a lot of optimizations that we want to do. So it sort of seems obvious to say values aren't nullable, end of story. On the other hand, what if we want to migrate local date time to be a value type? Those are already nullable. And there are some there are some classes that really would like to have protection against being used uninitialized, like allocating an array of something and then using the element without initializing it. So one of the things that we've been kicking around, and we have no great answers here, but we have some okay answers that might lead to a better answer, is to give authors a choice of saying, okay, no matter what you do, the default value of your value type will be these all 0 bits, but I'm going to give you, the value type author, the opportunity to interpret what that means. Is that just, a bunch of int zeros, or should we treat that as null? And null pointer exception if you try to dereference it. And so this is one of the things that's on the investigation list for L3 is this something we need? Is this the natural way to do it? Nullity is very much complected with almost all of the other characteristics that are going on here. It's correlated with but not implied by non-flattenability, for example. And so we constantly find null being used as a proxy for various things, and maybe that's a good idea and maybe that's a terrible idea, and we're still wrestling with that bear. Another interesting question that comes out of the L-World hypothesis, which says that everything is an object, is, okay, what does the equal operator mean? Well, currently, for all the types we have today, asterisk, asterisk, the equal operator means, are these two values substitutable for each other? Are these two references to objects references to the same object? Are these two integers, the same integer? And with the exception of, floating point nan, the equal operator is a substitutability test for everything we have now. So the obvious answer is to say that it should be a substitutability test on values as well. And that's a little uncomfortable, especially when you think about what the implementation means, and all the VM people in this room are groaning now. And we sort of have like two bad options on the table. One is to say equals equals just always returns false when one of them is a value. And that is something that a VM implementer could love, but it leads to anomalies like if O equals O being false. And that's not something programmers love. And at the other end of the spectrum, you could say, well, equals should be a substitutability test, and that's something that programmers love, but the VM guys don't like it very much. I see John shaking his head. He still hasn't gotten used to it 6 months later. So this is definitely a story to be continued, but this is one of the things that we have to confront when we've said, okay, everything's an object, great. Well, there's a bunch of operations that we expect to be able to do on all objects. Equals comparison, locking, identity hash code, weak references, and we need to have a story for each of these things, and the stories for most of them are uncomfortable. So another thing that's coming up in the future discussion department is, what do we want to do about migration? We have a number of classes like optional and local date time. They're just itching to be values. When we were writing them, we knew they wanted to be values, and it would be a shame if we couldn't migrate them to values. On the other hand, this has a lot of challenges for both binary and source compatibility. There's plenty of existing code that assumes these things are nullable or instantiates an array list of optional or what have you. So this is another one of those sticky problems that we will be spending a lot of time exploring over the next few months. And like I said, there's other things that come along for the ride. What about locking? What about identity hash code? What about weak references? And again, more discussion. So, okay, where are we now? We're in a pretty good place. Despite all those open questions that I talked about, folks who are building data structures or are building compiler runtime libraries can start using this now and start hopefully getting results like the crappy benchmarks I showed, in the middle of the talk. And we still have a lot of things to discuss. We have to validate that this is the programming model that makes sense for people. We have to address questions like, do people need finer grain control over flattening, which some people might deride as wildcards on steroids? And we have to come up with sensible stories for nullity and migration and specialization. And right now we have support in C2, but we don't have support in Graal. So there's a lot of missing pieces. But like I said, we're at an inflection point where we actually have, instead of theory and slides, we have a working implementation that you can write programs with. And so my call to action is, we're ready for early adopter experimentation. This room is full of early adopters. So, if you do interesting work with data structures, if you do interesting work with language runtimes, please try it out and report your experiences. And, tell us what works, tell us what doesn't work.